Okay, so I'm now recording, and I'm going over the implicit differentiation worksheet that I put in the A and D period Schoology groups. For A period, it was under post-session files, and for D period, just right in the front of the Schoology page. So anyway, when you ask to take the derivative with respect to x, that's exactly what we're doing, right? We're just doing d dx as an operator on each side. D dx as an operator on each side. So the left side is going to be 6x squared. The right side is going to be 4y, but you got to put dy over dx. And of course, root of 5 is just 0. So why do I do the dy over dx? Because when you're doing d dx of something in terms of x, like x squared, right? The derivative of x squared is 2x. And technically, you're also doing this. It's kind of like where did that extra x go, right? If I have x squared and became 2x, the x just vanished in the ether. Technically, what happens is that notation-wise, you're seeing this, but that just cancels because they're the same thing. So we don't really write it because it's redundant, but that's what it is. It's 2x. Now, what if I do d dx of y squared? Okay, use our power rule, so it's 2y, but then the y that went away latches onto the d dx like this. And that's why we need to have that, because we're doing it with respect to x, but our variable was in terms of y. So that's what's happening there. And then algebraically, you just isolate dy over dx and you're done. And that's what you're doing. And so if I isolate dy over dx, easy peasy, I get 6x squared over 4y. 6 over 4 you can reduce, 3x squared over 2y, and that's it. You're all set with that problem. And sometimes some people get kind of lazy, like I get lazy every once in a while. Instead of writing dy over dx, you could also write y prime. I don't really care. In fact, actually, when you're at this step over here, especially when you got a really nasty implicit differentiation problem, if you just want to write just a 4y times y prime, that's fine too. I'm okay with that. That's not a problem. And AP folks who grade it, they're fine with it too. And then the answers are shared at the end of this file. If we go all the way down, there we go, 3x squared over 2y. So we'll ask for my D period students, I'm going to put in a breakout session in just a sec. Go ahead and just keep doing more of these. If you want to skip around, that's totally fine. If you want to kind of divide and conquer among the other people in the breakout session, say, hey, can you do 2, 3, I'll do 4, 5, and we could talk about it. However you guys want to do it. I will admit that the ones later on are more challenging, especially when you have a product with X and Y in it, because then you have to do a product rule. So be mindful about that. Number 10 and 9 and 10 will actually involve a chain rule as well. So those get even more fun. I'll probably talk about when I bring you guys back in the breakout session, just to see how those went for you. And 11 and 12 are also kind of cool because there's natural log and sine. So check and make sure you're comfortable with those derivatives. 13 and 14 are even more intense. Those are second derivatives. So you gotta do it once and then again. That's kind of what they like to do in the AP exam, especially in the free response. They want to make sure you can mechanically handle that. And then 15 is a bit more critical thinking problem, which I haven't really thought through yet, but they're giving you different strategies to try. I guess they all give different answers. So yeah, I guess it shows why the order kind of matters of how you do things. Actually, you should get the same answers if you do all. Let me just look at that one more time. Actually, interesting. You do get different answers. Never mind. Some of the terms, got it. They actually are all the same. Got it. Yeah, so order actually wouldn't matter, but it's just some are in terms of one, some are not. Got it. Okay. That's kind of weird, but don't worry about it. Just do the other problem. So again, for D period, I'm going to put you guys in a breakout session right now. So let's create a breakout rooms. Let's do one breakout room. and I'll sign manually. So let's see, we'll put Alex, Ella, Ellie, Hadley, and Ian. Evelyn, Gabby, and Katie and Zoe will stay in here in the main room. So I'm going to teach them parts of 5.4, the leftover topics they need to see. So open the room and let's set this for 18 minutes. Okay, so you guys will go. Okay, welcome A period. So just give me a second, I'm just gonna grab some drink from the kitchen. If you guys can pull up the 5.4 notes, let me share my screen again. So the 5.4 notes are right here. I did go over this last time. I'm gonna kind of jump ahead to wait. Oh, this is optimization. I'm sorry. This is optimization, not related rates. You know what? Let's do related rates. I'm gonna skip around a little bit. So actually, if you guys can go to the 5.6 notes instead, and you actually can locate that. If you go to, I didn't realize I have my sections mixed up. Let's do let's do related rates instead. So I'm gonna actually reverse things a little bit, just because I talked about implicit differentiation, and I think that just might be a little easier to deal with right now. So if you do go to lecture notes, the whole lecture notes, even all the leftover topics are all right here. So you'll see 5.6. So go to the 5.6 notes, which I have open right now. So I'm going to talk about the beginnings of this, and then probably get to the end of page 2 is my plan. So it's something that's covered often in you know, a lot of calculus, even non-AP classes. So I'll be right back. Hold on. Okay. So related rates. So again, let's just do a review of chain rule and some implicit differentiation as well. So these are 5.6 notes. So let's look up to the right here, this little dialog box. You're doing d dx an operator of x squared. We know it's 2x. Technically, it's also times dx over dx, but we don't really care to write that. This is 2y squared, sorry, 2y. We got to write times dy over dx. Now look at this one. This one's interesting. You have s squared and you have d dt. So obviously these variables are different. Like, you know, the x and x, those are the same, but x and y, those are different for the second one. So d dt of s squared. So that's going to be 2s times ds dt. And that's going to be kind of a big deal because a lot of the problems to deal with here will be in terms of time, where we take derivative with respect to time. So here we're going to differentiate both sides with respect to t using the chain rule. So for example 1, that's going to be 2s times ds dt. That's going to be 2x times dx dt. And that's going to be 2y times dy dt. So we were asked to differentiate with respect to time, or t, and all the variables I had in my equation, for example 1, s squared, x squared, y squared, none of them were in terms of t. So you had to do the d whatever over dt. You had to do that because none of your variables are in terms of time. Well, they're all functions of t, but the letters themselves didn't have t in them. So you had to write that. So let's do the same thing for example 2. That's dv over dt, because root of v is 1, but we got to put dv over dt. And then you got to be careful here. You're going to have to do a product rule for r squared h. So you take derivative of r, which is 2r. We got to say dr of dt, then times h, of course, plus r squared, derivative of h is 1, times dh over dt. So, yeah, there we go. Questions about 1 or 2 before I move forward at all? Okay, let's do it again. So, again, we're doing respect to t. And this is a little nasty here. So you have 3 things being multiplied. So what I probably would do is I probably would lump it like this. You could also lump the y and z or x and z. It doesn't really matter. But take derivative, get dv of dt. And then I'm going to kind of write this first. xy prime times z plus xy times z prime. And off to the margins here, let's work out xy prime. That's going to be 1 times dx dt times y plus x, and the derivative of y is 1, but times dy dt. And of course, we got to still this other part, this xy in parentheses times z prime. But now when I work it out, I got dv over dt equaling, then in parentheses, I'm going to write y times dx dt plus x times dy dt, and of course times z, plus xy, and derivative z is just 1, but times dz dt. And if you want, you can leave the answer that way, or distribute the z into that giant parentheses that you see there. But the bottom line is that the answer is going to look kind of like this. Let me type this up as a text box up top. Do this in a different color. So it's going to be dv divided by dt equals yz parentheses dx dt. Space things out a little more nicely. Then you're going to have xz dy dt plus xy dz dt. Okay, so the text box up top where I have the title of the section, that's what you should be getting. Seems a bit orderly, which is good. So again, this is just practicing doing chain rule / implicit differentiation. Question about example 3. Okay. Let's skip number 4. That's a bit redundant. I really want to kind of get to the heart of the matter here, especially because I got called in the other group in about 9 minutes. So let's skip example 4 and let's go straight to examples 5 and 6. And then I will make a video on the rest of this that you guys can watch, and then I'll give you guys problems to do over the week. And then we'll talk about it next week. Then we'll probably go back to optimization next week. And then we'll talk about linearization. And then we'll talk about, there'll be 3 more leftover topics by the middle of March. So example 5. Spherical balloon, spherical balloon is being inflated at a rate 10 cubic inches per minute. How fast does the radius of the balloon increase when the radius is 4 inches? Okay. Well, spherical balloon, this is how you could probably draw a sphere. Okay. So here's R. Now, usually what you want to do as a strategy is what equation relates volume and radius for a sphere. So you always need to know, you always need an equation. It's called related rates for a good reason. You're looking at a relationship among variables, and then you want to look at how those rates are related. That's why it's called related rates. You're doing a spherical balloon, and you've got to look at the units too, cubic inches. Anything that's cubic is going to be volume, right? Now, don't worry about geometry formulas. I'll give them to you. Well, actually, I'm not even testing anymore. We're done with the semester. You got your grade. But on the AP exam, I think usually they'll, maybe kind of, I don't know. I need to find out. But don't worry so much about memorizing crazy geometry formulas. But V equals 4/3 pi r cubed. That's the volume of a sphere. So that's the first step. You need an equation. The next step is then you got to take a derivative with respect to time. So that's dv over dt. And 4/3 pi is just a constant, so you kind of just push it off to the side. Derivative of r cubed is 3r squared, but you got to say dr over dt. dr over dt. Now, the next step is a substitute. So there's 4 steps actually, 4 steps. The first step, you need an equation that relates to everything, depending on the situation you're given. The second step is you do the calculus, do the derivative with respect to time, which is easy. That's implicit differentiation. That's why I started that worksheet today. The third thing is you got to substitute the stuff you're given. So you're told that the rate of the volume is this. So this is a rate, and this is volume. This is dv over dt, if you haven't realized that yet. And then this is r, so this is at a certain snapshot. At a certain moment, at the moment, r equals 4, how fast is the radius changing? This is the whole point of the problem. If you've ever blown a balloon, you'll probably notice that initially it's probably not moving too fast when you blow it because it takes some time. And then once it expands and we start blowing more, you'll notice that the balloon has a faster expansion at that moment. Something I realized when I do this for my kids because they like playing balloons. So anyway, we got to substitute, and actually I should have cleaned stuff up a little bit. I didn't realize these 3's cancel here. So then you substitute the stuff you know. So it's increasing, so it's being inflated. So that's a positive change. So that's 10. By the way, if you're deflating, put -10. But you're inflating, so it's increasing volume. So it's a positive change. 4 pi, the r is 4 at this moment. And you're trying to solve for dr over dt. But ask how fast the radius is moving, how fast is increasing. Dr over dt is what we don't know. And then the fourth step is just algebra at this point. 10 equals 4 pi times 16 times dr over dt. You could divide everything by 64 pi. And don't forget the units. It's going to be inches per second. Sorry, inches per minute. And on the AP, you don't have to simplify. You can actually leave like this, but as a multiple choice, they'll probably have it simplified as 5 over 32 pi, So anyway, so that's what happens there. That is a related rates problem. Let me show you the summary of steps, and I'll go back and spend more time if you need me to. So read the problem carefully. What is changing? What remains constant? This has a 6, 7 steps. I don't know if you really need to do 7 steps. Really, steps 4, 5, 6, 7 is what I care about. But 1 and 2 and 3 are kind of good if in case the situation is complicated. Like read it carefully. So what's changing? What stays the same? Like we had a radius, we had a volume changing. We had a diagram of a balloon or a sphere. Okay, fine. We had it labeled. Usually 2 diagrams are good. One general and one that's very specific for the moment that you want to see how things are changing. Like when R was 4, I probably should have made another diagram for that. Identify what you got to find. Okay, do I have to find a dv over dt, dr over dt, whatever. So there's a lot of prep work you got to do before you start getting to the heart of the matter. Then this is why I said what were the 4 steps really. You need an equation. You got to take a derivative. You got to substitute stuff that that you're given, and then solve. And you always wait till after you do a derivative to substitute the step. Never substitute beforehand. You always got to do the derivative first. So steps are all laid out here. Now this one, we might be using all 7 of these steps for this last example here. So you got a highway patrol car that's on the y-axis. You got a guy who's running from the cops. He's got balloons. Highway patrol officers in a police cruiser approaching a right angle intersection from the north is chasing a speeding car that has turned the corner, is now traveling straight east. So the police car is going south, of course. He's coming from the north, but he's traveling this direction, and this car is going that direction. The police cruiser is 0.6 miles north, and the speeding car is 0.8 miles east. This is from the intersection. And the officers determined with radar that distance between them is increasing 20 miles per hour. So we're actually going to draw a right triangle here. So I'm going to call this Y. I'm going to call this X. I'm going to call this Z. So when the officer uses radar, so the officer has a radar gun pointed towards the car, he notices the car is, the distance between them is increasing. So that represents dz over dt, just so you know. The police cruiser is moving 60 miles per hour. That's going to be dy over dt. However, because y is losing value, because the police cruiser is getting closer to the point intersection, so the distance the police cruiser from the intersection is losing value, you're going to say it's negative 60. That's a tricky part. But dz over dt is 20 because you are told that rate's increasing. So you have to be mindful about what quantities are changing and how they are changing. As time passes, that side length y, is it getting bigger or smaller? It's getting smaller. Of course, x is going to be getting bigger. And so dx over dt, I don't know. That's what I want to find. What is the speed of the car? That's what I want to find. So you got to do all that prep work. And a snapshot, a second diagram. So the police cruiser is 0.6 miles north of the intersection. The speeding car, the green car, the balloons, is 0.8 miles from away from the intersection. So using Pythagorean theorem, that's going to be 1, just so you know. This is using Pythagorean theorem. And that's going to be our equation. So now when we actually get to the heart of the matter, this is the equation that you're working with. This is what relates everything. Take the derivative, which is really easy with respect to time. So 2x times dx over dt plus 2y times dy over dt equals 2z times dz over dt. So all the stuff in red was all the prep work. I had to read through the problem. I had to label my diagram, draw another diagram as a snapshot. This right here we call the snapshot. At a certain moment, we want to know how fast the speeding car is moving. What rates am I given? What rates I need to find? Blah, blah, blah. So you got some prep work you have to do. The stuff in black is now the heart of the matter. This is actually technically step 4 on the next page. What I was calling as really the first step. Make an equation, take the derivative, substitute stuff you know. So 0.8 is x. Let's keep those rooms open for just a little bit. dx over dt, of course, we don't know. Y is 0.6. dy over dt, of course, is negative 60, as I said so. Z is 1. And dz over dt is 20. And then you just work it all out. 1 point, and then you got to do the algebra at this point. That's going to be minus 72. I think, is that right? Yeah. You divide by 1.6. And you get the speed of the speeding car. It'll be miles per hour. So that is going to be a related rates problem. Very common type of. There's also one that deals with like a ladder that has Pythagorean theorem, a sliding ladder. That's also a very common one. But you get 70 miles per hour for a speeding car. There's one with a cone that deals with like pouring liquid. That's gonna be more challenging, but I'm gonna do a video on that for you guys. And there'll be some textbook problems. There'll be worksheets. There'll be Albert I/O. So I'll have some time to have things updated by tomorrow morning. And then the plan is for you guys to do some work over the weekend. You come back next Wednesday, see if you have any questions, and then we'll do optimization 5.4. And we'll just keep the cycle going. So again, lots of modes of learning. You know, you got me on Wednesdays. I'm going to do live lessons. You got videos on stuff I don't quite get to within that section. You got textbook problems all assigned. You got worksheet problems all assigned. You got Albert I/O that I'm going to assign. So you're going to get lots of modes. Albert I/O is good for AP style problems, practice there. Textbook more the rote. Works is more the rote. Textbook problems to kind of beef up your critical thinking a little bit. And of course you have, and then the notes, of course, I'll have the notes available as well with the videos. Okay, so let me go ahead and clear this. Let me bring the other guys back. Close the rooms. Because I think we have 2 more minutes before you guys gotta hop into another breakout session or another AP study group. By the way, the next AP study groups, they start precisely at 9:45 or at 10 o'clock?
9:45.
Oh, geez. And then how the one after that at 10:15 or 10:30?
I don't remember.
Okay. Goodness.
I just figure it out as it goes.
Yeah. Okay. Okay, cool. So any questions from the D period students that work on the implicit worksheet problem that you guys want to ask about? They may have found a little confusing or...
Do you want to do number 9?
Sure, I'll do it really quickly and I'll wrap it up. So what you do here...
There were a huge chain of problems in that one.
Yeah, so derivative left side is easy. That's just 6x squared. Then here you got to do a chain rule. So you got to move the 2 to the front and drop the exponent by 1. But then you got to do the derivative of that inside part. So a little accent mark there, right? Now let me do that in red. So that's going to be 3 times 1 times y plus 3x times 1 times y prime. And derivative of 1, of course, is just 0. So when you have 3xy, you got to do a product rule with that. Derivative of x is 1 times y. Derivative of y is also 1, but you got to put a y prime because you're doing it with respect to x. So you bring it back into the fold. So 6x, let me go back to black. And you got to isolate y prime, obviously. So 6x squared equals 2 times 3xy, darn it, plus 1 times, and that's 3y plus 3xy prime. At this point, you're going to have to distribute, or you could probably divide the 2, I'd say. 3x squared.
Oh, that is smart.
Yeah, I'd probably do that. And then, yeah, it's kind of messy, but given the fact it's 9:45, you guys can get to your next AP study group. You got to, or I guess you could divide by all this and then subtract the 3y and then divide by 3x.
Yeah, that really sounds better.
Yeah, and the answer is going to be kind of weird. It's going to be different, but don't worry so much about the isolating part. Just make sure you can actually do the derivative part. That's what I care more about. The algebra, it's not like that's really nasty, just so you know. You're not going to see anything quite like that. So, but if you could do like the beginning problems, you know, I'm cool with that. So, but I think 9, I think 6 is kind of reasonable. You know, something like that. Maybe 7, or 8, but yeah, 9 and 10 I think are a little much.
Okay.
Okay. Cool. I'm gonna stop the recording.